Hello students, we are ready with our next video. In this video we will discuss different type of first order and non-first order spectra and different terms used for them. Let's see here. This is a compound. We can see here 1 chloro, 2 1 chloro, 1 dichloro, 2 chloro ethane. As you can see here, there is one proton, there is two proton. So this type of compound is called AX2 spectra. This proton is called A, and these two protons are called B, X, and they're called AX2 spectra, indicating A is this and this is X. Why do we call it AX2? We call it AX2 because they are very well separated in their NMR spectra, as A and X are very well separated in their alphabetical order. So what is the meaning of AX2? AX2 meaning is that they are very well separated in their NMR spectra. Similar is the case of as A and X are very well separated in their alphabetical order. So AX indicate first order type of spectra. So AX2 spectra. So in this case we will observe for this proton we will observe triplet. For this proton we will observe doublet. This is a bromoethane. CS3 CS2Br. So CS3 CS2Br indicate A2X3 type of spectra. So again this is spectra which is a first order type of spectra, A2X3 type of spectra. This is 2-chloropropanoic acid, 3 CS3 CHCOH. This will appear at very high delta value, so around 10 to 12. So it is called AX3 spectra. AX3 spectra is called first order type of spectra. This is an example of cinnamic acid. Cinnamic acid is C6H5CHCHCOH. So it will appear at very high delta value. High delta value is around 10 to 12. It is A and it is X, so it is called AX type of spectra. So in this case we will observe for the CS3. In this case we will observe for this proton we will observe triplet. For this proton we will observe quartet. For this proton we will observe doublet. For this we will observe quartet. For this we will observe singlet. For this we will observe doublet. For this we will observe doublet. For this we will observe singlet. So it is A or X type of spectra. So this is 1 chloro, 2 bromo ethane. So CS2Br is the example of A2X2 type of spectra. It is the example of A2X2 type of spectra. So AX type of spectra indicate first order type of spectra. So they will show us the formation of two triplet, one triplet for this and one triplet for this. Triplet for this will appear at high delta value, it will appear at low delta value. This is 4 amino phenol and 4 chlorophenol. We can see here, if I ask you how many type of protons are there, only two type of protons are there in benzene ring system. One is this and one is this for benzene ring system. Otherwise 4 type of protons are there, 1, 2, 3 and 4. For benzene ring system there are only 2 type of protons. So these two are same, they are called A. These two are same, they are called B. So it is example of AB type of spectra. So it is example of, we do not call it A2B2, we call it AB type of spectra. We call it AB type of spectra. Again here 4 chlorophenol. We can see here these two are same and these two are same. So A, this is B. So this is called AB type of spectra. So these two are AB type of spectra. For this compound we will observe doublet. For this we will observe doublet. So doublet for two protons, they will appear at same delta value. Doublet for two protons, they will appear at the same delta value in the range of benzene ring system around 6.5 to 8K. We will observe this value around 6.5 to 8 for these proton, around 6.5 to 8 for these proton. This will show doublet for this. So doublet for one proton means two protons. So for this spectra we will observe doublet for two protons, doublet for two protons. So these are called first order type of spectra, and this is called non-first order type of spectra. Now we will discuss NMR spectra of aromatic compounds. We have discussed with aliphatic compound how they show different type of peaks, what are the different peak pattern. For in case of aromatic compound, we just start with simplest compound, toluene. Toluene is the simplest compound, as we can see here. There are 3 proton. there are 3 proton, so we will get 1 peak for these 3 proton and 1 peak for these 5 proton. These 5 protons are accidentally equivalent, so these protons are called accidental equivalents. They're called accidental equivalent protons. So proton of benzene are called accidentally equivalent because they are by chance. It is by chance they are appearing at same delta value. Otherwise, they should be showing us 1 peak for this, 1 peak for this, 1 peak for this. But because the electron activity effect of R is not very strong withdrawing, not very strong donating, therefore they have a moderator effect. So therefore all of the 5 protons appear at the same delta value, and they're called the accidental equivalent protons, proton of benzene. So what will be the spectra of benzene? This toluene is singlet for this CS3, singlet for these 5 protons. Remember the intensity of the peak. This is a small peak, this is the large peak. The intensity of the peak always depends upon the ratio of the protons. If ratio of the protons are higher, then intensity of the peaks are higher. You can see here ratio is 3:5, similar as the ratio of the peaks 3:5 ratio. So we should take into consideration that intensity of the peak, whether they're strong peak or a small peak, depend upon what is the number of proton in that environment. If protons are 2:2, so peak intensity will be same, 1:1. If protons in one environment proton is 1, in one environment proton is 2, so intensity will be 1:2. So intensity of the peak depend upon the number of proton in that environment. So for 3 proton we have this 3 approximately. For the 5 proton we have this larger intense peak for 5 protons. If we have this paraxylene type of compound, in case of a compound where group is para substituted and group nature is same, no matter it is electron withdrawing, electron donating, if group nature is same, suppose I instead of this CS3 I place here NO2, I place here ClCl. So whatever is the group nature, if they are same, ClCl, bromo, nitro, CS3, if they are same and they are occurring at the para position, in that case all 4 will show us the same chemical shift value. All will show us only 1 proton environment, so we get only 1 peak for the benzene ring system. So we are considering the paraxylene system. So paraxylene system, 1 peak will be for singlet for this 6 proton. So we are having singlet for 6 protons at high delta, at low delta value and high intensity. It will be approximately around 1.2 or something like that. So in case of benzene ring system, we will observe a singlet peak for 4 protons. So we are getting 4 proton, a singlet peak at high delta value in the range of benzene ring system around 6.5 to 8. Similar is the case with this orthoxylene. Orthoxylene, these 4 again are accidentally equivalent. So we are again observing example of accidental equivalent proton. So these 6 will show us a singlet and these 4 will show us a singlet. Ratio 6:4. So this is the spectra of simplest aromatic compound. These are some examples of aromatic system which contain group which are strongly electron donating or electron withdrawing in nature. So we here observe here nitrobenzene. Nitrobenzene, in case of nitrobenzene, we will not observe the accidental equivalence because these 2 are different, very much different, and these 2 are very much different, and this one is very much different. In case of bromobenzene, these 2 are very much different. These 2 are very much different, and this is very much different. These 2 are different, and these 2 are different. So in case of aromatic compound where group R is strongly electron withdrawing or donating, accidental equivalence will not be observed. So nitrobenzene, in case of nitrobenzene, we will observe a complex pattern of aromatic peak pattern. We will observe a complex aromatic peak pattern for complex because these A proton we are assigning as A will couple with this B and will also couple with C. So in case of aromatic system, you should remember one point here is that in case of aromatic compounds, long long range coupling is also observed. What do we mean by long range coupling? In case of a simple coupling, we observe coupling between neighbor. Only neighboring coupling is observed, or neighbor to each other, they couple easily. But in case of a vinylic system, in case of a allylic system, in case of a benzene ring system, not only group which are ortho to each other, but group which are meta or para to each other can also couple due to the closeness in the aromatic system, and the aromatic system provide the closeness due to which they start influencing. This proton start influencing the environment of this proton. Not only this influences this will also influence this, and this will also influence this. So this will also influence this, and this will also influence this, and this will also influence this. So we observe a complex pattern of spectra in case of an aromatic compound because of the long range coupling with ortho, not only ortho, with meta, with para also, in aromatic, in vinylic and allylic system. So we observe a complex pattern, but you can see here in nitro compound, NO2 is the electron withdrawing group, strong electron withdrawing group. So it will make the A proton, A positions, strongly d-shielded position. So we should expect a peak pattern for HA will be at a higher delta value. So we are observing high delta value, a complex peak pattern for high delta value HA. Then we observe HB and HC pattern. So we observe a pattern of 2 proton. It had, then we have peak for 3 protons. And complex pattern, we cannot make out what is the nature of peak. We cannot easily define whether it is a peak singlet, doublet, triplet. We cannot define that. Singlet, doublet, triplet, we cannot define it because they are so overlapping, so complex. We just appear them as a bunch of peaks. So similarly, we can take in example of nitro compound. We can also consider the same example with benzoic acid. Benzoic acid will also show us the same type of pattern where we observe 2 protons separated by 3 protons. In case of orthobromo proton or orthobromo benzene, here again same type of pattern will be observed. HA appearing at high delta value due to the electron d-shielding, then HB and HC. So we observe a bunch of peak for HA followed by HB and C to 2 proton separated by 3 proton peak patterns. In case of orthodichlorobenzene, we observe again peak, a bunch of peak, but what one thing we should note here is that whether it is orthodichloro or whether it is bromo dichloro or whether it is a nitro, dinitro, dichloro, dinitro, orthodinitrobenzene, if they are chloro, chloro, bromo, bromo, nitro, nitro, so in that case we observe a bunch of peak, but peak pattern will show some symmetry. We will observe some symmetry in the peak pattern. Due to symmetry in the molecule, we will observe some symmetry. You can see here, this is a mirror image of this type of peak pattern. This is mirror image of this peak pattern. So we observe some type of symmetry in case of a orthodichloro, orthodibromo, orthodinitro benzene ring system compound. So these are the complex spectra observed in case of aromatic compounds. So after discussion of these some complex pattern, we will, I think it must be clear to all of you. So we will meet in next class. Thank you.